great. Okay. Yeah, great stuff. Okay, yeah, I'm Julian Fletcher. I've been involved in the Great Western Railway fast charge battery train project since 2020, when I moved to work at Viva Rail, as was Adrian Shooter's company. And at that point, it was a sort of concept, I suppose. And my job was to come up with the charging system that would connect the train to the power supply. And I'll come on to the thrilling details of that in a moment. So there it is, that's the battery train over at Greenford. So it all started with the train as was taken up to the COP26 conference up in Glasgow in 2021, in November. Now you may know that the battery train is a London Underground District Line D78 stock train, converted by Viva Rail. There's a number of them around. They were running Bedford to Bletchley, but then when Viva Rail went into administration, they were taken out of service, and so Great Western actually owns them now. But there are other Class 230 and Class 484, which are basically very similar trains operating. The 484s down in the Isle of Wight, they're a third rail pickup, and the 230s for transport for Wales, they're a battery hybrid with a diesel genset. So the little train that you can see there is just a 3-car unit, trailer car in the middle, driving motor cars either end, and there is pure battery power. There's no other source of energy to go with the train. And that unit, as was back in 21, that was with what we call the next generation of lithium-ion batteries on it, and these were capable of being fast charged. And I can answer detailed questions on what that really means later if you wish. But when we went up to the COP26 conference, we didn't have the fast charge system designed or the shoe gear ready to go. So we just charged up from the depot, and off we went and took guests around at COP26. But it was always destined for the Greenford trial. So that's where the Greenford branch is, just running from West Ealing and back. And the train is stabled at the West Ealing Light Maintenance Depot. So once the train was developed and built up, we put the fast charge equipment on it and put the GWR livery on it, and did testing at Long Marston, and prior to that a bit at Bletchley. And then next step really was to do some mainline testing before taking it out on the mainline for real and going down to Reading and then subsequently to West Ealing. So it's the first time we'd really tested how the batteries would behave going at any distance, because we could only potter around the loop at Long Marston. So but we were very happy with it. You could drive it very economically, and we did quite a few miles. I think it was 86 miles in total, and we only used about 45% of the battery. So conservatively, I'd say you can do about 120 odd miles in it. Some of it was downhill, to be fair, but it's of that order. People often ask, how much juice have you got on board? How far can you go? Again, we'll come on to that in a bit more detail later. So at the moment, we're operating up and down the branch. That's the charging system over on the right, and in the middle, the upper one is, you can see that big cable. That's one end connected up to the depot charger. There's a slow charger back at West Ealing, and that's in the depot, not at the fast charging location. So just to put that in a bit of context, the fast charger at West Ealing platform 5, we've set it to charge at around 650 kilowatts there or thereabouts in total, and the charger at the depot is about 50. I think that's just there because it looks pretty. So the project as a whole, let's talk about where we've got to. I mean, the purpose of it really was to put the train through its paces, put the charging system through its paces, and also look at lining up the energy modelling with what you get in reality. So to do that, clearly you need a system installed and operational. You need the train to be compatible with where you're going to operate it and approved. So there's an awful lot of work in just getting a train to operate on the railway, as you well know, I'm sure. And then once we've got the train there and we've got the charging system working, just basically plugged in and working normally, then that's where kind of my test plan came in, the 12-month test plan, and we kind of throw everything at it. I think in theory, if we did every permutation that I initially planned, it would be up to about 33,000 tests. We whittled that down to about 50 because clearly we didn't want to be there until we're all expired. And we're coming towards the end of that now. We've got through an awful lot of permutations covering weather, driving style, auxiliary loads, all sorts of things. And we're also in the process of training drivers so that we can carry passengers in May. That's the plan. So a bit about the exciting bit, the fast charging system, which is unique to the train. It's not unique in being a battery carrying train. The Transport for Wales have got battery trains in the core valleys and they charge off the overhead. But ours charges using the little ground-based system, and you can see the charging rails there, and that funny little sort of brass webbed thing there is the surrounding structure around the carbon copper composite charging shoes. So here's a bit of a simplistic view of how the charging system works, but it is actually quite a simple setup. So the energy for the whole thing comes from the grid connection from the main supply. So there's a DNO connection box, big green cabinet at West Ealing, but that's only trickle charging the fast charge battery banks that sit at the track side. There's one battery bank for each end of the train, and each end of the train charges independently. Each battery bank is fed with around, I think it's a 45 amp trickle feed. It's rated to 63, but as again, I don't want to insult your intelligence, but 45 amps is not a lot. It's about half of a shower's worth. You know, it's half of a, sorry, not a shower, half of a house's worth. So generally, you class it as a small industrial supply. Downside of that is when you're trying to install one of these things and get it hooked up, you are nothing more than somebody else on a list to the DNO. So, but on the plus side, we did get connected eventually. And so these battery banks are 20-foot shipping containers. There's two of them, and each one is then connected to the charging rails, but they only go live when the train is present and a set of interlocks are met. That's quite important because it's very different to other systems which are live pretty much all the time. So the way it works is that we have 3 RFID tags in the forefoot. One tells the train that it's in the right location. One tells it to lower the shoe gear, because the charging shoe gear, it stays retracted. It's pneumatically operated, and it stays retracted well out to gauge during normal operation. But when it comes into charge, it's deployed when the train goes over that RFID tag. And then finally, when the train is in the right location, then it goes over the last RFID tag to initiate the fast charge. At that point, there are also proximity sensors, and they are the hardwired safety interlock to allow the fast charge to proceed. And here, a very stunning cartoon which shows kind of how that works. The RFID detects at the front of the train, and so at first you watch all the little green lights go on inside on our little monitoring station, and then we see it lower the shoes. You can hear the shoes go down, and then when it's in location, then the charging rails then go live. There's an initial ramp up of current, and providing that's all within parameters, then we'll put on full power and charge the train. So to put that in a bit of context, the plan right from the off was that the battery train would operate as a cut and paste of the diesel operation. So same timetable, same turnaround times, all that sort of thing. So we designed it such that it could charge up in the 4 minutes that it takes for the driver to change ends and go again, and it does. So it's quite an efficient unit, and it's an extremely powerful charger. And now hopefully we've got a little bit of video taken from when we were first testing the system at Bletchley. So you'll see on the left here, there's 3 sort of stubby charge rails. They're much shorter than the real thing, and that's because we just didn't have enough space. And also this big sheet of nylon here is just put over the concrete pad, because you'll see it's quite a lot higher than the running rails. So when the shoes come down, they just crash into it, which is not really representative of where the train will be operating. So we didn't want to break them. And if you look carefully, you'll see the shoes coming down, and they kind of skid along the white plastic. And then they ride up the ramps, and then the train starts charging automatically. There we are. And I must admit, I think we've done somewhere close to 400 fast charges with the train now, and everyone is still exciting. Before we put the fast charge system on the train, I wanted to make sure that the fast charge shoe gear system was robust enough for the job. And this is a little rig that we built with a couple of track rat trolleys. So you can see there's 2 there. There's the one sort of nearest us and the one towards the back. The one on the back is strapped down, that's stationary, and the one nearest us here, which has got you can just about make out the shoe gear that's bolted to it with the blue air pipes coming out the front of it. That is propelled along the track by an enormous pneumatic piston. Now, we needed to reach a target speed of about 5 miles an hour, and it weighs about a quarter of a ton. So when we did the maths, I was fairly keen for us to achieve that speed so that we could then do repeated cycles and put it through a mechanical endurance test program. So we needed to accelerate in a very short time period and a very short distance. So we had quite a powerful actuator, and after we first switched it on, it nearly disappeared into the next postcode. So the challenge really was how to slow it down in a controlled way as well. And you can see we've got sort of mechanical buffers there, and a lot of the control system actually is focused on slowing it down, putting on a bit of reverse, and then depressurizing the whole system. And but it worked, and we did about 20,000 cycles on the prototype system and about 14,000 cycles on the production system. So the charging system over at West Ealing, that's got trackside battery banks, as we mentioned, and you can see over on the left there's 2 shipping containers, as we mentioned, one for one end of the train and one for the other. Within those containers, they're split roughly halfway, and one half has got the batteries in, and then they're all contained within a firewall, and they've got fire suppression and the rest of it. And then the other end is the AC connection. It's worth bearing in mind that all the batteries in the systems that we use, be it on the train or on the track side, are all closed loop thermally managed and remotely monitored. It's pretty standard with lithium ion these days, and not really much of a problem. They're used well within their operational capability, and they're not too hard to control. So we usually get asked, well, how long are the batteries going to last, and what do you do with them? Now, we need to be clear that this is a trial, so we've got first life batteries both in the train and on the track side. In the shipping containers, there is no reason that we couldn't use second life batteries in the trackside equipment. They'd be a little bit bigger because the energy density would be lower, but basically we could wait until we use some X traction batteries. That's a very neat sort of closed loop. Or you can just get hold of second life batteries, but they are in such great demand, ironically, and first life batteries are lasting so long that it's there isn't a massive economic compulsion to get second life batteries at the moment, just because they get snapped up so quick that demand is outstripping supply. But to just give a broad picture of lithium-ion batteries and how things are in terms of their degradation over time, it depends. This first life, it depends very much on the chemistry, but these days you're talking 10 to 15 years. I think Siemens are quoting 20 years for their lithium titanates. I'm expecting at least 10 years from ours, and then they'll be ready for their second life in a stationary storage application, and then recycling beyond that. So I touched on the modelling and the prediction of energy consumption. The simplest question really is, well, how far will the train go? And we touched on that initially. So normally you'd say, well, you could go about 75 miles. We've upped the regen since these numbers, so that's actually a little bit, well, it's quite substantially more than that now, but the kind of message is the same, which you'll see. So that's our Class 230 train. There's a nominal, let's say a nominal range of around 130 kilometers. If you then crush load it, it's quite noticeable that you don't make that much difference putting a load of passengers on, mainly because you got the benefits of the steel wheel on rail, and you recover a lot of the energy through regenerative braking. If you put the heating on, however, that's quite substantial, and that takes greater effect when you combine that with a timetable. So an interesting note there. If you limit your speed, you can really up your range, just like with a car. But then if you stop every so often, then you have to accelerate the vehicle again. So you kind of start throwing away energy, and it gets worse if you stop very frequently. And as you might imagine, the train at West Ealing stops quite frequently. If you put a gradient on there, that has quite a significant effect if you're not careful, especially if it's a big gradient. And our operation is somewhere over here, so it's not horrific, but it's not, mainly because of the stopping pattern, it's not super efficient because you just have to fulfill the timetable. So we know what the range is, but we also need to know how the energy is taken from the battery and the rate at which it's taken, because then you can start to look at how the thing's going to behave in service and how you could use it elsewhere. So, I mean, we've called it our battery train network simulator, but it's something our graduates developed, and it's because we've had so much data to play around with while we're testing the train, we've then been able to develop this. So we see a lot of people have got energy consumption simulators and developed this kind of a tool because it is just a bit of physics. But what we've done is then use measured data off the train to make it far more kind of robust and realistic. But you can do multiple trains, multiple routes, multiple charges. So this is something you'll see this kind of graph plotted. Lots of people do it. They just get into Excel and put in Davy's equations, do a little bit of physics, and away you go. You've got your energy consumption for your train, and you'll be somewhere close, but you really need the real thing to see how the efficiencies of all the components interact with each other. But you can see this is fairly typical. We've got the left-hand plot shows the speed versus the time, and then the right-hand plot that's showing the behavior of the traction batteries and I think the fast charging system as well. So you can predict how the state of charge goes up and down each time using this tool. but then you really want to educate it with the data, which I shall show you in a moment. So the trial itself, what results have we got from that? We'll probably see this kind of an image come up on the media quite a lot, because people like it. It's pretty and it shows what the thing's doing. That's one of our sort of easy to use front ends, and we've done quite a lot. We've looked at extremes of weather, and that does include where you, for example, if you're running on a very hot day, so the HVAC systems on the power electrical systems are working hard, and then you work everything deliberately hard to try and get your really high currents flowing, and find out where that corner is, find out what your worst case energy consumption is with all those kind of parasitic loads. Similar in some ways for the cold weather, and we've run the thing in a pouring rain. That's all right. Deliberately laid up leaves on the charging rails. West Ealing is got a lot of trees around and a lot of leaves, and so that was fun, but it worked okay. Lots of degraded operating modes, if you like, and as the guy kind of running the test, I didn't win a lot of friends for all this, but I do like to properly explore what happens when you switch off half the train and run like that until everything's on its knees. And likewise, the charging system, just turn half of that off, see how you get going, how things degrade, or turn the whole thing off. We ran without regen for quite some time, and that was slightly deliberate. And then when we put it on, we had a real clean back-to-back. So the train has excellent regen, but we also know what it'll do when that's not functioning. We've done some high passenger load tests. We ran with 102 people, about 10 tons worth of people. It's always fun, anonymously weighing people as they come on, but you have to be very, very quick. And we checked the height of the train when we did that as well. And it feeds into the energy calculations because you've got to accelerate the mass and decelerate it. And we've got a crush load test coming up in April to really get the final point where we're looking to put 250 people on the train, so it's going to be pretty cozy. Driving styles has been fun. Can't beat telling a train driver to just floor the thing, and they love it. So that's been an education. Driving it like you stole it is probably the most efficient way to drive it, which is slightly counterintuitive, but there's subtleties in there, but driving style does affect things quite a bit. And stranded train operation, we get a lot of people worrying about, well, what if you get stuck at a signal forever? So it's not really a problem. It's got a lot of battery on the train, and we run a lot of back office monitoring of what state it's in. But basically, as soon as you get to West Ealing from the depot, and you charge it up, and it stays like fully charged. It's fully charged, down about 6%, back down, and it recovers as much as it uses. You'll see that. That's next slide. So actually, your standard train situation is not a problem because you can last for with the heating full on hours and hours. So I think we've done 3 separate tests, one at 70% state of charge, right down to 40% state of charge, which is kind of worst case, just about to leave for the depot, something's broken, all that sort of stuff, and it's fine. And to put it all in context, if you switch off the heating, you can have a stranded train for about 2 days, so you've got bigger fish to fry by that time. So we mentioned about the state of charge of the batteries. FCBB stands for Fast Charge Battery Bank, and there's 2. There's one for what we call the London end of the train, the leading car, and one for the trailing end, the country end. And this is very typical. You see they start at a very high state of charge, and they just go up and down a little bit each time, charging up a little bit, and then the train takes them out, and then they charge up a little bit. So track side, that's happening. On the train itself, you can see the train leaves the depot usually around 85%, which is basically full. We don't charge it to more than 85%. And and you can see it just sort of drops down as we approach West Ealing, fast charge, juices up, and then drops down as it goes to Greenford and back, and then juices up again. You see up, down all day long. So that's pretty typical. In terms of looking at the modelled behaviour versus the measured behaviour, we've taken all the different factors that come in there and looked at how they're understood on the model, and you can see the red line is kind of predicted behaviour, like state of charge versus time throughout the day, and within the grey band is how things vary depending on all the different conditions that vary. So we have a good idea of how we can be confident about saying what energy you need on your train and how fast you need to charge it. And that's really quite a big deliverable for this, because if Great Western or anybody else want to run a battery train somewhere else, the first thing you'll kind of ask yourself is, well, how long have I got to charge it? How powerful is my charger and how big is my battery? But really, it's all about how powerful is your charger and how long have you got. Again, it's a slightly downbeat tone of these slides. Oh my God, how are we going to stop running out of battery? But this is how we do it in the back office. It's constantly monitoring how far we are from the depot or from where we've got to go, and how much juice is in the tank. And you see the little yellow bar, as we progress time-wise. So if you're a bit further away from depot, you need a bit more, hence the spikes. And as soon as you're closer, you need less. And so you just monitor the two, and away you go. And I think if I include next slide, but you can monitor those two things as they degrade, and you can automatically deal with it. So the idea that the driver has to worry about range and anything like that is not something we do at Great Western. We will monitor it automatically, and we get emails to ourselves at the moment, but we get communication set up with the operations team to manage the range of the vehicle. But as you saw, it's not really a problem. So lower carbon, why do we care? What's the point? I mean, we may as well, if we're not interested in carbon, may as well just keep the diesel going. So we do need to look at this and actually say, well, what isn't it bad for the environment that you're fitting batteries to it? They produce carbon and all that sort of stuff. So we worked that out. We worked that out before we took the train up to COP26, because the one thing I did say to the team at Viva Rail was, you cannot take a train that is claimed to be environmentally friendly up to the COP26 conference and have somebody come on board and say, what is the carbon footprint of this vehicle, and not know the answer. We had to know the answer. And so we worked it out. You work out what materials have gone into it, how they're processed, how much carbon emissions are associated with them. And also you say, well, okay, that's all the materials. What about all what we call scope 3, all the emissions that are produced around making the thing? So you might spot 25% of the emissions of building that vehicle were due to the gas heating of the factory. Stunning. So if you want a low carbon vehicle, do it with some in an environment that's heated efficiently, and various other bits and bobs in there as well. So all in all, usually we quote around 250 to 300 tons of carbon, because it depends where you put the boundary on that. Personally, I'm recalculating it every 6 months to say, well, this test we're doing now contributes to the embodied carbon of the vehicle in total. But as you can see from like fleet vehicles and travel, they're relatively small beer right now, and we are down into the roundings at the moment. So 300 tons, 255 tons, 300 tons, how does that compare with the emissions from the existing diesel unit? So light green is the cumulative emissions from the battery train, tracking along year on year, assuming it goes into service this year. And you'll see here that actually the emissions there are higher at the starting point than the DMU, because I've said, well, look, we've built this thing, therefore we need to bolt about 250 tons on top of any emissions that are due to the electricity that's being used. Therefore, that green bar there, the light one at the beginning, is higher than that of the diesel. However, within 1 year, the diesel has put out more emissions than the combined effort of the battery train and its embodied emissions that have gone into the battery, all that gas we burnt to build it, all that stuff. So the idea that these things have got so much embedded carbon that they're not worth it is actually total nonsense. And this is very typical. Other branch lines, it's even better. You know, you knock it out within about 8 months. So the general message is the sooner you bring these things in service, the better in terms of your emissions. You'll spot the yellow circle in the middle. That's because after around 10 years, you may need to change the traction battery. And if you really squint, you'll see there's a slight step up in the light green bar. That's due to the embodied carbon of the replacement batteries. So again, not a big player. What I have done is, in terms of the electricity used to charge the train, I've banked the UK grid efficiency improving, or should I say the UK grid emissions improving year on year. As per the graph on the right, that's a pretty conservative take on things. If you Google it, you'll find there's people far more optimistic than that. There's also people saying we'll be down to 0 by 2040 and all that sort of stuff, but I've tried to pitch something that's fairly sensible. So, oops, let's see if we can go back. Don't appear to be able to go back. There we are. Yeah, so air quality is another benefit, and we've got air quality measuring kit at West Ealing. And you see on the left is the light green bars show the timetable for the existing diesel unit. And the dark green are the nitrous oxide emissions measured on some kits that was actually bolted onto the trackside battery banks. So it is quite some distance away from the train itself. We're going to do some on the platform as well, but you compare that to the graph on the right, it's exactly the same scale, same time frame, but on a Sunday where we were running the battery train, the diesel wasn't running, and everything falls into the background, except the little spike at whatever time that was. I think that was 2:48. So yeah, if anybody knows what's happening on the 1st of December near West Ealing at 2:48, I don't know whether that was the Class 66 is going past or not, but anyway. So yes, that's how we got it done. And yeah, I think it was a happy combination really of having a team that Adrian Shooter rustled together, and he told us in no uncertain kind of terms that we would get this thing done, and also the fact that at that point in time battery technology was suitable to go on a train, and also that we had a charging system to charge it up at the right power within the right time scale. So if you put those three things together, you end up with a battery train that fast charges. Now within those people with the can-do attitude, I would put a shout out to the Rail Adventure drivers. They've been excellent and very tolerant of me just wanting to switch stuff off and muck about with things, and likewise the folks at Fuse Rail who have been equally supportive and really do kind of get the project. So I think the slides aren't moving along particularly fast at the minute. But I think that's the slide pack as it stands, because I think there's usually quite a few questions, so I thought it'd be good to allow a decent amount of time for that. So thank you.
Thank you very much, Julian. Does anyone have any questions for Julian?
There are a few questions in the chat, though.
I can't actually see the chat, so if someone can read them out for me, that would be wonderful.
Can you see them, Julian?
No, I can only see Mark Hambley's at 1535. I can't see more.
Okay. So I'll just read these out then. So you might have already covered this, Julian. So
Okay.
apologies if you have. What is the expected or tested battery temperatures? Is that really bad for the batteries?
Oh, sorry, just was that a question about temperatures and batteries?
Yes, yes.
Yeah. So, I mean, the batteries are thermally managed on the train and on the track side, but the cells on the train are pouch cells. They're great big pouch cells, about A3 size, and they're arranged like fins, and they have air blowing over them, and then that air goes through a heat exchanger, and they're both heated and cooled depending on what we need to do with them. So that keeps them within their optimal sort of operating temperature, typically around 20-ish degrees, and the current you can draw from them is controlled. So when you there's certainly enough to get the train going in the morning. There's no question of it not moving or anything like that. But we do control how much current can be drawn or put into the batteries depending on what the temperature is. But like I say, the temperature of the cells is controlled on closed loop, so that's usually not a problem.
Okay. Another question here, again about the batteries, about length of viable use.
Mm-hmm.
And it just gives an example. If a train drives 400 miles and charges 3 times every day, and 200k miles, that's 500 days of use. So that's under 2 years. Would the batteries need replacing sooner?
Oh, right. So we do about 155 miles a day, but the life of the battery from the supplier is termed in amp hours of use. And unfortunately, I like to mix my drinks a lot in terms of battery behavior. So we only charge it up by about sort of 6 or 7%. So in context, it's 500 kilowatt hour pack on the train. So 10%, that's 50 kilowatt hours. So yeah, we put in about 35, 40 kilowatt hours per charge. So when you work that out in terms of a timetable, it works out at around 8 to 10 years. But what's actually happening in real life is that the cyclic life of lithium-ion batteries up until very recently has been based on quite a harsh charge-discharge cycle, and that's all you do. You sit them in a lab, charge and discharge them all day long. What you don't do is fast charge, then quick acceleration to get out of the station, naff all as you coast, and then a little bit more of an acceleration to regen, and these basically a little spiky demand, and then back to the depot, and 6 hours, 5 hours, 6 hours of nothing, or just steady background slow charge. And the most recent research, as from last week, I think, is that kind of behavior has unexpectedly been beneficial to battery life, like significantly beneficial of the orders of tens of percents or 20, 30%, that kind of thing was what people are quoting. So and it's usual, it's really unusual, because in engineering, stuff just doesn't work out that way. Things don't last longer than you expect, not a lot longer. So that's taking folks by surprise, but it's becoming normal. So I would say that this train's batteries will be lasting for around 10 years plus, is where my money's on. Maybe a bit more. Okay. Ask me in a few years' time, I'll see.
And then just as a follow-on to that, using the fast charge, does that have an impact on the battery itself? Would the battery degrade quicker if you're using the fast charge more frequently?
If you didn't control the temperature, then yes, it would. when you get into the nuts and bolts of batteries and the anodes and cathodes and the electrolytes and the behavior and how they degrade, how they wear out, a lot of it is due to internal degradation, and people talk about lithium dendrites growing, which is basically where you put so much potential across the battery and it just hasn't got the time to react to that. So instead of actually passing ions from one to the other, it actually, you start to physically grow little dendrites of lithium. And the way to do that really is put tons of current across the thing and let it get hot. So if you or do when it's really cold, because it's extremes of temperature are what stop it doing what it wants to do. So provided you control the temperature to the optimum temperature, to 20 odd degrees, then it doesn't actually have an effect. So and I suppose, to put it in a bit of context, the system, we've designed it to be able to charge at I think it's about 3.5 C. So in English that means about 1800 kilowatts, so nearly 2 megawatts, but we only charge at about 650 kilowatts. So we're using around a third of the charging rate that the batteries could use if we wanted to.
Okay, good stuff. Mark Hambley, he's asked whether you've considered using as an alternative an overhead pantograph arrangement.
Very good question. Yeah, I mean, you can do pretty much the same charging from the overhead, and most manufacturers are looking at around the 2 megawatt mark for charging trains off the overhead. And this system was developed specifically as a drop-in for where the local power supply wasn't suitable for the overhead. Either connecting up to it existing overhead wasn't easy, or getting a power supply in that we could use for a 25k wasn't easy. But you certainly could. There's many of the GWR routes will long term have battery trains charging off the overhead, and that's what TFW doing down in the core valleys. So yes, absolutely. I mean, clearly you carry a transformer with you, but that's not a particularly big deal. We've been doing it for years. So yeah, you could charge them off the overhead if you want to. I guess a little bit of context of part of the ground-based charging system, it has it's got pros and cons compared with overhead. It's very safe because it's switched off unless the train's there and it's all interlocked and going. And NetRail said, it must not be live if you've got any line of sight on it, which you haven't really. And also you charge it using battery energy storage. So you can plug that into renewables, you can charge it off peak, you can even do two-way energy trading. That is all normal these days. You buy batteries in a box and you can go and let them pay for themselves. That's business. Those business cases exist. So it kind of unlocks the connection between the rail industry and this clean technology world where energy management is always intelligent and smart. You don't get a battery powered vehicle which is not smart at the moment. That's just not quite how it works. So, and it's quite quick to install. I mean, Dan will tell you it's not a disruptive thing to take possession and install the charging system. We have had to have a few goes at it because we were learning. Certainly there are bits about exactly where to position it, but that's part of the trial. So compared to the OLE, it's quick to chuck in. It's quite safe. It's quite cheap, quite simple. Not many stakeholders to upset, but it has its place, has its limits, and the OLE can certainly be used to charge a battery train there. Yeah.
Good. So Michael asks, when are battery trains coming to the Marlow and the Henley branch?
Oh, what an exceptional question. Yeah. What am I allowed to say? If you know that I'm trying to work out what I'm allowed to say, then you can probably guess what's going on.
Should we move on? Right. Okay.
But,
Michael King asks, how does the weight of the battery train compare to a diesel equivalent? And do you have a view on access charges and impact on maintenance?
Yeah, well, yeah, very good question. So the batteries on this train are the best part of 10 tons against a 95-ton train, and passenger load when you crush load it is 25 tons. So that's on top of all that stuff. So it's in the roundings because we've taken about 6 tons of diesel kit off. So I think we're what, 4 tons up, perhaps, Matt, perhaps something like that. So the increase in axle weight isn't a lot. I mean, it is there, that's for sure. You're certainly hanging off some lumps off the underframe, but we are talking kind of the order of less than 10% in terms of total train weight. So not really too much of a problem. Access charges are the same as with the other 230s. So it's very similar to the 165s, the diesels that they run. What was the second part of the question? Oh, maintenance. I remember. Yeah. Yeah. Well, maintenance is all usual running gear in terms of suspension, brakes, that sort of thing, windscreen wash. But I would say it's like a carbon copy of a normal OLE powered train, because on an OLE you've got the pantograph as the moving component that goes up and down, that needs servicing. Likewise, we've got the shoe gear that goes up and down and needs looking after. It's pretty reliable, but it's something to keep an eye on. The batteries themselves don't really need much doing to them. They're remotely monitored and you just plug them in and let them go. Really, they have a cooling system on them, so air cooling then gets heat exchanged into a glycol system, but the glycol system and HVAC on it is pretty off the shelf. So other than checking that for leaks, no real problem there.
Good stuff. Stephen Bell asks, are you hopeful that sorry, just going off my screen. Are you hopeful the technology can continue to progress to a level where battery trains could operate fully on remote lines such as the West Highland and Far North?
Yeah, absolutely. I mean, I think there's about across the country, there's around 30 locations where this kind of setup could work on your short branch lines, and where they're remote, but you have got access to a trickle of power that you could charge up a trackside system. So yeah, absolutely. Yeah.
Good stuff. And then there's James who's just asked, thank you, Julian. I thought it was an interesting talk, given that I'm an apprentice for the OLE, and I do think that it's useful to have the alternative solution to overhead line due to the costs. How much would we be looking at cost saving in using the fast charging train and installation of the charger mat? And that's specific on the Greenford branch.
Yeah, that's a good question.
We do come up with good questions in this section.
Yeah. So I mean, because the maintenance costs, like I say, they'll be similar to the 387. The OLE cost per, I think the package is around a quarter, roughly. I'd say around a quarter of what it would have been to fully electrify it. Now, how you spread that over how many years of operation is interesting. Yeah. I mean, I guess that the one thing is it's certainly comfortably less. Let's put it that way. Where it gets interesting is you can't really choose where you get your diesel from. Whereas if you store your energy trackside, you can choose, do you want to get it from, let's say, a load of solar PV on the car park at Waitrose across the road? Do you want to just have it off peak? You could just use off peak juice, and suddenly your electricity price starts to collapse. So whenever you're looking at the cost of the system, it's I always say it's an opportunity cost thing. And as I know Dan pretty well, and he knows what goes on in my life at home. And once you get into the world of clean technology, once you get an electric car, then suddenly you're like, oh right, what's the minimum cost for me maintaining this and powering it? And maybe I'll only charge it off peak, and maybe I'll get some solar on the roof, and maybe I'll do this, and all these things start to come your way, and they only send the cost in one direction. So the baseline cost is less. Now we have to be a bit careful. These are old D78 trains, so they haven't got as much life in them as a new train, but they're not going to be burning a massive hole in Mark Hopwood's pocket, put it that way.
Good. Okay. Well, I think that's all the questions answered. So thank you for that, Julian. I'll pass you back to Dan.
Right.
Yep. Thanks again, Julian. Thanks everyone for those questions. They were very good. Just a quick question from me, if you don't mind, to bring it full loop back into the Ashford type area. As you know, the third rail is prominent in Ashford and the southern, and it has tendencies to freeze and have ice on top of the rails. And then we have a conductor rail heating system to help alleviate that. This is a bit of a loaded question because I know the answer, but it's interesting for everyone here. Have you looked at the formation of ice on the charging rails and how it impacts charging?
We have. Yeah, it's very interesting. So we might need a charge rail heating system. At the moment, as you know, we did a icing test at West Ealing, and we put a lot of ice on the charging system, and arguably we probably over-egged it, and so the system didn't really like that. So that's slightly contradictory to the rig test that we did, where we put a sort of heavy frost of ice on the system and ran it mechanically, and then just checked the impedance, and it all looked okay. So somewhere in the middle, I suspect, is kind of worst case British requirement plus some margin for extremes of weather. So I think the mitigation would be a heated rail. What we do need to do is a bit of additional work to say, well, are we absolutely certain? I think, in all honesty, I'm teeing up the team for a bit more work to do some more testing and look at the standards, look at real weather trends, and beyond West Ealing, and say, right, out of all the locations this could go, what does it need? Is it mechanically capable enough to push ice off, or do we need to heat the thing?
Very good. Okay. Just a quick reminder from me that our next meeting will be on the 17th of March, and it will be with Dan Mason of Military Workshop. Details will be published once we have everything confirmed. And I'd like to pass over to Colin to give the vote of thanks on behalf of the Ashford section.
Yeah, thank you, Julian. A very informative presentation there. I know I speak on behalf of the section when I say I found it very educational, so thank you. I guess this all ties into the sustainability topic. And, if we look at the automotive trade, we talk about range and battery life and all the rest of it. And within the rail sector, we talk about investment from a sustainability point of view on the infrastructure, and that can be, concrete and steel and all the rest of it. But it's refreshing to see, the rolling stock piece being tackled as well. And I can only say it's going to grow arms and legs and become more and more prominent. So thank you for your presentation. On behalf of the Ashford section, I would say thank you and well done.
Well, thank you very much for having me. I appreciate it.